Okay, we're going to move into the next type of bonding that we're going to talk about, and that's covalent bonding. And this is the sharing of valence electrons. So let's look at the word covalent. Co. Well, if we look up co on the internet in some type of dictionary, we're going to see that co means together or sharing. And valent, the root word valent, refers to valence electrons. So when we look at covalent, if we're going to actually define the word covalent, covalent bonding is the forming of bonds between nonmetals where the atoms share electrons to reach full octets. Now look at this word nonmetals. Okay, let's compare this with, say, ionic bonding, where ionic bonding is a bond between a metal and a nonmetal. Covalent bonding is a bond between two nonmetals, so it doesn't involve a metal at all. So it's bonds between any of the elements that are on the right-hand side of the stair-step. So let's look at a common covalent molecule, which is water, H2O. So we can see here that the red sphere is representative of oxygen, and the two black spheres are representative of the hydrogen. So the hydrogen is bonded to the oxygen, and we use these little lines, this stick drawn between these two molecules, to represent that bond. Well, what exactly is happening here? Well, if we look at the valence electrons, we know that oxygen has 6 valence electrons. So here they are. And we know that hydrogen has 1 valence electron. But they're wanting to get to a full octet. Now, remember, hydrogen is the exception. Hydrogen only has 1 orbital, and only 2 electrons can fit into that orbital. So to have a full orbital for hydrogen, it only needs 2 electrons. So what happens here is this electron is going to be shared with hydrogen. So hydrogen is going to think that it has its own electron, and since oxygen is going to share this one, then it thinks it has a full octet. I'm sorry, a full, not octet, because octet means 8, a full outer shell. Same thing with this hydrogen. It has its own, plus oxygen is going to share this one. So it thinks it has a full shell. Now what's happening with oxygen? Well, oxygen has its own 6, but it's going to share this one with hydrogen, and hydrogen is going to share this one with oxygen. So now oxygen thinks that it has its own 6, plus this one that's being shared from hydrogen to make 7. But there's 2 hydrogens, so that makes oxygen think that it has 8. If we count the electrons, 1, 2, 3, 4, 5, 6, 7, and 8, oxygen now thinks it has a full octet because those electrons are being shared. And the way we depict the sharing of electrons is to draw a line between these 2 atoms. Well, let's look at some common examples of covalent and ionic bonds. Now remember, I said earlier when we're talking about ionic bonding that hydrogen, even though it's on the metal side, is not a metal. Hydrogen is the exception. It is a nonmetal, so it belongs over by helium. Okay, so let's look at ionic bonds. Sodium and chlorine. Well, sodium is a metal, chlorine is a nonmetal, so that automatically makes this an ionic bond, metal, nonmetal. Okay, lithium is a metal, fluorine is a nonmetal, ionic bond. Iron is a metal, oxygen is a nonmetal, ionic bond. Magnesium is a metal. We could stop right there. We don't even have to look at this SO4 because if it contains a metal, it is an ionic bond. Okay, now this next example here, you might look at this and say, well, this is nitrogen. That's nonmetal. Hydrogen is nonmetal. Carbon is nonmetal. And oxygen is nonmetal. So this is a covalent bond. But if you were to say that, that would be incorrect. Because remember, we have this list of elements that come together and bond together that have a charge. And that's called a polyatomic ion. And if you look at your polyatomic ion list, you can see that NH4 is a polyatomic ion. It has a charge. So this automatically makes this an ionic bond. And if you didn't recognize C2H3O2, that's an acetate ion. It's on your list. Okay, so we have two polyatomic ions here that have formed a bond, ionic bond. Now NH4F, again, you have to recognize that this NH4 is a polyatomic ion, or you're going to get this wrong on the test. So although you don't have to memorize that polyatomic ion list, you have to be able to recognize the polyatomic ions when you see them. All right, let's look at covalent bonds. Nitrogen and oxygen are both non-metals. They're on the right-hand side, so neither one of them are a polyatomic ion. N2H5 is not in a polyatomic ion, so that makes this a covalent molecule. N2H4, again, hydrogen is a non-metal, so this is a covalent bond. Now, SO4, you may say, that's a polyatomic ion, so this is just a polyatomic ion. But in order for it to be an ion, it has to have a charge. So we see SO4 here, but it doesn't have a charge here in the upper right-hand corner, so it's not an ion. This is a covalently bonded molecule. Okay, CH3OH, carbon, hydrogen, and oxygen are all nonmetals, so this is covalent. Okay, CH3, we need two of those. That's not a polyatomic ion. And CHOH is not a polyatomic ion. All of these are nonmetals, so it's a covalent bond. And water, H2O, both of these are nonmetals, so that is a covalent bond. Okay, now remember that all ionic bonds are called compounds, and covalent bonded atoms we call molecules. Okay, so there's the difference. Compounds, we've already talked about compounds. When we have a covalent bond, those are called molecules. All right, so let's look what happens when we dissolve these in water, an ionic compound and a molecule. What happens when we dissolve them in water? Well, when we said that ionic bonds form lattice or crystalline structures, this is what we mean. If this is, say, salt, the red sphere here represents the sodium, and let's say the green represents the chlorine. Well, we see here a positive cation, negative anion. Well, this negative slightly attracts this positive, but it's not going to bond because it's already been bonded here. So this negative chlorine is going to attract this sodium, and so on and so forth. And this sodium is going to attract this chlorine. So they wiggle and they form this crystalline, very organized crystalline structure. Whereas molecules do not do that, because they, just the way they're bonded, they don't form a crystalline structure because they have things sticking out everywhere. But when we dissolve these in water, we can see that the sodium chloride, it's going to break up into separate ions. So you're going to have the sodium ions floating around in the liquid and the chlorine ions floating around separately. They're going to be unbonded when you dissolve them in water. It's going to break those bonds. However, when we dissolve a molecule in water, the molecules unclump and separate from each other, but the bonds between these separate atoms are not going to break. So this is what happens when you dissolve sugar in water. Now this is not sugar. This isn't representative of sugar correctly, but we're going to say this is what happens when sugar dissolves in water. The molecules separate. And when we would dissolve salt in water, the actual ions separate. So that's one big difference. So let's write our vocabulary words down. We defined covalent as sharing of valence electrons. And if you ran out of room on page 5, you can go ahead and continue these on page 6. And let's define the word molecule as two or more neutral atoms that are being held together by sharing of valence electrons. All right, so let's discuss naming real quick. Naming, when you name a covalent molecule, you will use a prefix for the first element only if that element has more than one atom. And we're not going to change the name. Just like in ionic bonding, we're not going to change the name of the first element. But we will use one of these 10 prefixes if there's more than one atom. Okay, so the prefixes are, for number 1, mono, 2, di, 3, tri, 4, tetra, 5, penta, 6, hexa, 7, hepta, 8, octa, 9, nona, and 10, deca. So please write those down. And on the second element, when we name it, we're always going to use a prefix. And we're going to change the ending to IDE just like we do in ionic bonding. So let's look at a few examples. Here we have BrO2. Well, Br, it's bromine. There's only one of them, so we're not going to use a prefix, so it's just going to be bromine. The second element is oxygen. There's 2 of them, so if we look over here, 2 is di, and we're going to change the ending to IDE. So it's bromine dioxide. Bromine dioxide. Okay, the second one, there's only one of the first atom, so we don't use a prefix. Now remember, the second atom, we always use a prefix. There's one. If there's no number here, it's understood that there's just one. So it's mon, it's oxygen, change the ending to IDE, oxide, monoxide. So this is carbon monoxide. You may have carbon monoxide detectors in your house. This is a poisonous gas, and you don't want to breathe this because it will cause death. If you have a carbon monoxide detector in your house, it beeps when it detects carbon monoxide. Carbon monoxide is created from your heater if you have a gas or electric heater that for your central air conditioning in your home. If the burners or the coils that create that heat are malfunctioning, they instead of creating carbon dioxide, they'll create carbon monoxide. Release it blows that into your home, and if you don't have a detector and you breathe this, you could die. All right, moving on. First element. Now we have 2 here of this first element, so we're going to use a prefix. So the prefix for 2 is di, so this is dibromine. We're not going to change the name. Dibromine mon, there's only one, monoxide. So this is dibromine monoxide. And here we have a little bit more complicated, but it's not too bad. So there's 2 chlorine, so it's dichlorine. We have 7 oxygen, so 7 is hepta, and oxygen is oxide, so heptoxide. Now, we drop the A here because we don't want to put 2 vowels right next to each other. We don't want to say heptoxide. It's heptoxide. Okay, so that's as easy as it is.